Hello, I'm Pei Yi, one of the co-inventors for the AI-powered hybrid structural health monitoring smart damage detection. This technological invention is led by Associate Professor Aya Dr. Ong, supported by IIRG grant, has been patented, and has a TRL of 324. Structural health monitoring, or SHM, is important to ensure structural reliability and public safety. According to a market survey by Markets and Markets, the SHM market is predicted to increase from $2 billion to $4 billion by the year of 2027. This increasing trend is mainly contributed by the increasing use of sensors in structures, IoT, and cloud systems. With the aid of machine learning, ML, big data analysis can be done to provide accurate prediction in the structural conditions. This has also led to an increase of demand for predictive maintenance solutions that allow early damage detection to reduce downtime and to save costs. Therefore, there is a demand for efficient and damage-sensitive ML-based damage diagnosis methods. Some of the key problems in existing SHM methods are: first, shutdown conditions are required during measurement, which will lead to unwanted downtime costs. Second, typical features collected such as temperature, pressure, and etc. do not have direct relationship with damage, thus insensitive to damage. Third, since damage events are rare, there will be insufficient damage samples for AI model training, which can negatively affect the prediction accuracy. Therefore, this invention conducts ISMA, or impact synchronous model analysis, for measurement without disturbing operating structures, uses compressed upstream transfer data to detect damage, and integrates model-based method to allow early-stage damage identification. Here is a short demo on how this invention works. The scheme starts by collecting baseline data from the existing condition of the structure as the undamaged data. Then it starts to monitor the structural health condition by detecting and identifying potential damages on structure. The first layer detects damage presence using the unsupervised machine learning method. If damage is detected at this first layer, it proceeds to identify the damage location at the second stage or second layer. When there is no trained machine learning model yet, due to insufficient damage samples, the model-based method, or mode shift assessment, MSA, is used to locate and also auto-label the damage samples for future model training. Otherwise, the supervised ML method, which is a trained ANN model, is used. This explains the hybrid model machine learning concept of this scheme for damage identification. Now, let's look into the performance of the trained model in identifying an undamaged case. It is shown that the scheme can detect it as an undamaged event where the data acquired is below the damage threshold using the unsupervised method. Next would be the performance of the trained model in identifying a seen or trained damage case. As you can see, the scheme can detect it as a damage event through the unsupervised method and also correctly locate the damage, which is at support 1. Let's see how is the scheme's performance when an unseen damage case happens. It is observed that it can detect it as a damage event and correctly locate the damage support, which is at support 2 using the MSA method. You can also see the large deflection at the support 2 in the first mode shape animation, showing the damage sensitivity of the model feature. This identified damage and the subsequent damage occurrence are then auto-labeled and also stored for future ANN model training. Let's see the scheme's performance when an unseen multiple damage case happens. It is shown that the scheme can also identify unseen or untrained multiple damages at the first unsupervised stage and their locations at the second stage due to the damage sensitivity of model features used. In summary, this invention has been tested on lab-scale plate-like and beam-like structures. It is also proven that ISMA can clean the upstream transfer data for damage detection, thus allowing the scheme to be used during operation. Quantitatively, the ISMA denoise upstream data has correlation scores of greater than 90% when compared to the benchmark or static upstream data. Principal component analysis or PCA is then used to extract the damage sensitive features for damage detection, and results showed accurate damage presence detection for both plate and beam-like structures. In terms of identifying unseen damages, the overall average accuracy for both structures is 92.6%. Lastly, this invention has also led to several publications in the last 3 years as shown. Thank you.